Okay, some little deductive reasoning, some if-then statements. So on the first two, it says, given each statement, write the converse. That's really hard to see. Write the converse. If the converse is true, write the biconditional. If the converse is false, write a counterexample. So on the first one, it says, if Ed lives in Texas, then he lives south of Canada. What is the converse to that statement, Stella? If Ed lives south of Canada, yeah. If Ed lives south of Canada, then he lives in Texas. If Ed lives south of Canada, then he lives in Texas. Is that true? So all we did there was we took Ed lives in Texas and he lives south of Canada and we flipped it. Okay, so instead of if this, then that, now we have if this, then that. Is that true? It could be true, right? But it doesn't have to be true. If Ed lives south of Canada, then he lives in Texas. What would be a counterexample to that? We're south of Canada, right? So basically Ed could live in any state and be south of Canada. So our counter could be Ed could live in Vermont. Okay, so remember the counterexample should be a specific example. It shouldn't be general and be like, well, most of the United States is south of Canada. That's general. That's just kind of stating why you know it doesn't necessarily have to be Texas. A counter is a specific example. So Ed could live in Vermont and still be south of Canada. That's statement number one. Statement number two, so this is a false converse statement. Statement number two, if x equals 40, then x equals, or 8x equals 40, then x equals 5. So here's my hypothesis, here's my conclusion. And if I flip them, how does it read? If x equals 5, then 8x equals 40. If x equals 5, then 8x equals 40. Is that true? Yeah, if x equals 5, then 8 times x equals 40. That's true. So if it's true, we want to write a biconditional. What are the special words that we include for a biconditional? If and only if. So now I'm going to drop the if and the then. And it doesn't matter, like I could go from the original statement in terms of the order of things, or I can go from the second statement in terms of how I'm writing it. I kind of like it the other way, to say 8x equals 40 if and only if x equals 5. There's my biconditional. But I could have also said x equals 5 if and only if 8x equals 40, but I just feel like it reads better the other way. It's almost like you're solving the equation. If 8x equals 40, not if, 8x equals 40 if and only if x equals 5. So I no longer have the if and the then. I've smushed them together with an if and only if. Okay. Our third problem here gives us a biconditional and asks us to write it as two conditional statements. Conditional statements means write them with the if then instead of as with the if and only if in the middle. So it says points are collinear if and only if they all lie on one line. So what's one if then statement I could make from that? If, go ahead.
If the points are collinear, then they're all on the same line.
Yep. If points are collinear, then they all lie on one line. Okay, that's one conditional statement. And the other conditional statement would be if, yeah, if all points are on one line, so I'm going to reword it a little bit to make it make sense. If all points are on one line, then they are collinear. Okay, so given a biconditional, I could write it as an if-then statement going either direction with it. Okay, let's talk about our homework. So you had homework number 10, also on deductive reasoning on these if-thens. Homework number 10. Find that. So on the first couple problems, it didn't ask you to state whether, you didn't have to do a counter or a biconditional, but you did want to go through and identify what's your hypothesis, what's your conclusion, and then that should have said the converse of each statement. And so the hypothesis is what comes after if. So on our first one, our hypothesis is an angle is 90 degrees. That's our hypothesis. Our conclusion then is it's a right angle. Okay, so part A is listing my hypothesis, part B is listing the conclusion. Okay, A, B. Then from that, I want to write the converse, which just means I'm flipping those. So if an angle is a right angle, then it's 90 degrees, written the other way. Is that true or false? That is true. So it says, is the converse true or false? It's true. Doesn't ask us to do anything with that. Our next statement, if it is October, then it is fall. What's the hypothesis? It is October. And the conclusion is, it is fall. This underline circle thing, you'll be asked to do that on quizzes and on reviews. So underlining the hypothesis, circle the conclusion. My hypothesis is it's October. My conclusion is it is fall. Now the converse to that would be, if it is fall, then it is October. Is that true? Not necessarily. Yeah, that's false because it's fall right now. Fall started on Tuesday, September 22nd. And it's not October, it's September. Okay. Then we have this table. So given the statement, write the converse, decide if it's true or false. So first statement's really similar to the one above. So if it's Halloween, then it's October. That's true. Halloween's always in October. But if I flip it and say, well, if it's October, then it's Halloween, that's false because, and my counter example is, October 1st is not Halloween. Kind of depends on your mindset though, right? I kind of feel like all of October is Halloween in my house, but it's not actually.
It's like a November's Thanksgiving. It's like a November.
Can I decorate for Halloween? No? Lawn decorations? What do you do? Yeah, and even people may not be able to come to your house this year. I'm still decorating.
Well, I mean,
Oh, nobody ever
You're
comes.
not gonna be able to.
Oh, Jaden's telling something. Do you decorate for Halloween?
Well, not this year because nobody's gonna be coming to buy candy.
Well, you can still decorate.
Well,
I'm gonna
it's
decorate.
like, I don't know. Kind of strange.
Our next statement, if an angle is 30 degrees, then it's an acute angle. If I flip it, it reads, if an angle is an acute angle, then it's 30 degrees. That's false written that way because there's many other acute angles that aren't 30 degrees. So just saying it's an acute angle doesn't mean it's 30 degrees. It means it's less than 90. Now, that can't be my counter. My counter can't be any angle less than 90 degrees is acute. My counter has to be a specific example. So a 31-degree angle is acute. There's my counter example. Last one, if an angle is a straight angle, then it's 180 degrees. Just a reminder from our vocab, straight angles look like lines. I have a straight angle and the rotation is 180 degrees. Okay, so if an angle is a straight angle, then it's 180 degrees. If an angle is 180 degrees, then it's a straight angle. Still true. Okay, it's true both ways. And so if it's true both ways, we can write a biconditional. An angle is a straight angle if and only if it is 180 degrees. Okay? How'd we do? All right, good. So now we have some pretty quick notes, and then I'll let you work on homework. We'll probably have time to go over that homework at the end of class too, which will be good because guess what we're starting today? Proofs. But they're kind of not real proofs right now. We're going to do some proofs, but link it to algebra class so it feels like familiar today. Come Monday would be a really, really important day to either live stream or watch the notes because that's when we are starting geometry proofs, which feel very different than algebra proofs. What is a proof? Yeah. Okay, so like your whole life in math, you're just like, here, solve the problem, and you solve the problem however you solve and you're done, right? A proof is exactly what it sounds like. We are proving, or we're providing evidence as to why we can do something in a math problem. Okay, so there's a lot of writing involved with proofs. We're not, it's organized a certain way so that anybody reading it can see, basically, I'm saying this is why I'm saying it. Now I can say this is why. Okay, so it's giving proof for your math work, but kids tend not to love them. But that doesn't have to be the case. They can be super fun. I think today's proofs are kind of fun. So we're starting, we're like tiptoeing into proofs. We're barely starting them today, and we're looking at some algebra properties. So one thing that we can use in proofs is that we can, when we have an equation, we can add the same amount to both sides of the equation. If you think of the balance beam, remember when you learned equations, you probably talked about balancing the equation. Okay, if I add 5 over here, I need to add 5 over here to keep it equal. Okay, now when we do that in geometry, it looks a little different, but like in algebra, it's like I'm solving an equation. So if I add 5 here, I have to add 5 here. Okay, so my addition subtraction properties, I'm gonna write it in the way we will use it when we get to geometry, is if A equals B and C equals D, then, see that if-then statement? Right, just like last class. If this is true, all right, so this is the same value. It's saying 5 equals 5. If this is the same value, then I could add it to both sides here and it would still be equal. That's kind of the general concept of the addition property. So then A plus C must equal B plus D, that if these are the same and these are the same, if I add these, it would be the same as adding those. That's our general property. It's a little messy. I'm going to give us 2 examples. One is like what we're going to do today. And then I'm going to try to create one that looks a little bit like what we would use in a geometry proof. Okay, so my first example is an equation. So in an algebra proof, if I have x minus 2 equals 6, then I know that x equals 8. The reason I know that is because I can add 2 to both sides. Okay, so do you see what I did there? I added the same thing to both sides, and C and D are the same value in the way it's written. In a geometry proof, give us a second example. Maybe I have a segment. Okay, so I have a segment, and I tried to make these look the same. Okay, I'm gonna label my segment. A, B, C, and D. I'm going to mark that segment. What do those tick marks mean? That they're equal. So I know, because of the way the diagram is drawn, and that I mark these tick marks, that AB is the same length as CD. Okay? So I know that AB is equal to CD. This is what the addition property looks like in geometry. Do you agree with me that I have BC in the middle, and that whether I look at this segment or I look at this segment, BC is the same length either way around, right? Okay, so I can say that AB plus BC then would be the same thing as CD plus BC. Again, let me give you a scale. I had an equation, AB equals CD. If I'm going to add BC over here, then I need to add BC over there to keep the equation the same. So all I did was I added the same amount to both sides. It feels different than adding the same amount to both sides here when we're solving an algebra equation, right? But it's the same property. I'm saying I'm adding the same amount to both sides. Now, who's going to be a geo whiz right now? Why would we want to say that? What then must also be true? I added the same amount to both sides. What's AB plus BC? AC. Yeah, it's a little segment addition. So I could also say that AC then must be the same length as BD. That's where we go with geo proofs. Yeah, Gemma?
Why do you need to count BC?
So the reason I'd want to do that, so let's say 2 classes from now we're doing a proof. It may give me the diagram and say, we know this is true, prove that AC and BD are true. So the way that I would prove it is saying, well, if we know these are the same, I add the same amount to both sides, now I can say those bigger chunks of that segment are the same, because I'm just adding the same middle chunk. Okay, that's why we would use that, is to be able to then say, oh, well then this must be true. AC must equal BD, that this segment from here to here is the same as this segment from here to here. So proof, when we get to geo proofs, that looks like a P. It's a D. When we get to geometry proofs, it's going to give us a given, and it's going to request something for us to prove. Okay, so sometimes from here to here, we need to put something in the middle to say why that's okay to say it. Okay, so it feels different, but really I'm just adding the same thing to both sides, just like I'm adding the same thing to both sides here. Now I only wrote the addition property down, okay? The subtraction property, I'll just add right above it. If this is true, then I can also say this. Or in other words, I could also subtract the same thing from both sides. Also use that a lot in geometry, especially with segments and angles and stuff. Okay, so we're going to live here today where we're comfortable, but these properties do come into play here in geometry class. Okay, multiplication property. Honestly, I'm trying to even think of a proof I've used multiplication property in other than algebra, so we'll just stick to algebra for right now. Our multiplication property, same idea. if A equals B, then A times a number is going to equal B times the same number. Or I can multiply both sides by the same thing and it's still equivalent. Or I could divide, or then A divided by C. I could divide both sides by the same amount and it would still be equivalent. So in algebra class, that looks like this. 2x equals 14. And I say, oh, that's 2 times x. So the inverse of that would be to divide by 2. And I'll do that on both sides. And x equals 7. Okay, that's what it looks like in algebra class. I can divide both sides of the equation by the same thing, or I can multiply both sides of the equation by the same thing. And then last one that we'll see today, and again, this would be primarily for an algebra proof, is the distributive property. So distributive property if we have a number outside our parenthesis, then I can distribute that number through, and what happens is that number gets multiplied by each term in that parenthesis. So I'm going to write a little mini proof here. Algebra proof. I'm going to say that step 1 that I have this. 2x plus 7 plus 4. Okay, that's, oops, I guess I need it to be equal to something. Equals equals 31. I think that'll work out okay. Okay, so there's my equation, algebra equation. This is what it's gonna look like, what we're gonna do. So first, I'm just gonna say that that's given to me. Next class, we'll stop writing the word given and we'll just write a G. That equation was given to me. Now, what are my two columns? They're not always marked. We can mark this. This is called our statements. So I'm saying this is true. And this is the reason that I'm saying this is true. So statements and reasons. So in our algebra proofs, we're just given an equation. So the reason I can state this is because it was given to me. Okay? The reason I can state this oops, that's not step 1, that's step 2. The reason that I can state that is distributive property. So what I did from here to here, and I don't show my work and like I'm not writing anything underneath or drawing in what I'm doing here, is because I distributed 3 through. So if I know this, well, I can state this because the distributive property exists. Okay, so what we're doing is we're organizing our work a little differently. Alert, alert. With something we're really familiar with. So we're really familiar with solving equations. We're starting here, but you see how it's organized a little differently. Now the next thing I'm going to state is this. And this is why I'm not going to finish this whole proof. I'm going to state that 6x plus 25 equals 31. What did I do there? I didn't, addition property is I took something and I added it to both sides. I didn't do that. All I did was combine these terms, right? So students get caught up there in terms of what to label that. That's a perfectly valid reason. Combine like terms. So it's a little different than what's above. I didn't add the same thing to both sides. I just said I have a 21 and a 4 here, so really I have 25 here. Okay? So I wanted to make sure you saw that. Many times it goes distributive property, then this, and then we'll solve from there. So let's do an entire proof here. I'm not done here. This would keep going, but I don't have space. Okay, I'm gonna write it the way, I think you'll see it in your homework. Let me double check your homework. Yeah, so the way most proofs are given to us is it gives us a given, and then it asks us to prove something. So this is gonna be my given, and I'm going to ask you to prove that x equals, or 4, equals -2. Okay, so I'm saying, I'm giving you this, prove to me that that's true, that x equals -2. And I'm going to prove that through some statements that I'm going to make, and I'm going to back up all of those statements with a reason. I'm going to have statements and reasons why I can say that. Now, my first statement is always the given. Making sure it's not Essex Elementary School. My first statement is always the given. 4x plus 3 equals 2, in parentheses, x minus 4 plus 7. That's given to me. I'm making this statement because I was told that that was my equation. It was given to me. From that statement, I can write a new statement. What would the next statement that I can make be?
4x plus 3 equals 2x minus 8 plus 7.
4x plus 3 equals 2x minus 8 plus 7. I had this. From that, I'm stating that this is also true because of the distributive property. And from this statement, I can state that 4x plus 3 equals 2x minus 1 because I saw like terms that I can combine. Okay, now comes the tricky piece. So now what I'm not going to do, and what we do in algebra class is we show like what we're doing underneath and we cross things out. I'm not doing that. I'm writing a formal proof. So I'm saying if this statement is true, the next statement that I'm going to make, and your statement may differ a little bit depending on how you solve the equation, but the next statement that I'm going to write is that 2x plus 3 equals -1. What did I do from here to here? I subtracted the 2x from both sides. My reason that I can state this is the subtraction property from up above, which tells me that if I have an equation, I can subtract the same amount from both sides. Okay, so I'm just going to write subtraction. Technically, it's the subtraction property of equality. We don't need that. Okay, we're just going to write subtraction. Okay. I had this statement. From it, I wrote a new statement. This is the reason I can do it. I have this statement. From this statement, I can write a new statement, and that new statement would be that 2x equals -4. Why can I say that? Subtraction property again. Yeah, I subtracted 3 from both sides. I can say this because of subtraction property. And from this statement, I can make a final statement, which is x equals -2. Division property. So if I knew that 2x equals -4, I divided 2 on both sides and I get x equals -2. All I did was division. Did I get to what it wanted me to prove? Yeah, okay, and you better, okay? There's no point of doing a proof if you come up with an answer that's different from what it's asking you to prove, then you did something wrong, okay? So we're starting with something familiar, but organizing it in a way that is like a geometry proof, okay? So I'm going to not give us any more proofs right now. What I'm going to do is I'll let you do homework number 11, which asks you to just do 2 algebra proofs, okay? And then we'll do them together. So I'll stop you in like 15 minutes and we'll go over them. And then before you guys leave today, I just want to go over Monday, Tuesday at the end of class, okay? That makes sense? Okay. And if online people want to stick around,